Okay, thanks everybody for coming. Today we have a special talk from Dave Jewitt, who's visiting us from UCLA. Some of you may know he was at the IFA for many years on Oahu. That's where I got to know him in grad school. And then a few years ago moved to UCLA. And the only other nugget I was going to throw out there is some of you may not know that Dave sat next to Inouye once on an airplane, former senator, and basically created got pan stars out of that. So that's what we have Dave to thank for pan stars. Go ahead.
That's not totally true.
It's not true. That's the legend.
I did sit next to him, and we did talk about astronomy, and I did ask about how would a person go about getting money for a new facility in Hawaii. And he just said, how much would that be? And I didn't really know. So I said, 20 million. And he said, shouldn't be a problem. And then then we had all these follow-up meetings. Then we figured out that University of Hawaii did not know how to talk to the senator. So they employed people, they probably still do, whose job was to kind of bond with the senator's office, but they were incompetent. And so we went off to this intermediate company, it's a parasitical intermediate company called SAIC. And they, in the end, turned out to be the ones who could talk to the senator because they employed the senator's former chief aide and a bunch of other people. So SAIC is plugged into this money machine just like crazy, and they got the money. Oh, anyway, okay, sorry, background. All right, so I assume that, you know, like me, most of you guys are here for the fun of it, right? Astronomy, fun, it's a good thing. So I am interested in unusual things and weird things, freaks of all sorts, basically for a good reason. First of all, they're just interesting. Second of all, you can learn a lot when you're surprised by something. So the exceptions to the rule are often much more informative than the rule itself. So that's the basic idea behind this title, which you already gave me your appreciation for. Thank you very much. Two freaks and a conundrum. So I'll talk about those things. It's going to be 3 talks, and they'll be individually short. I'll stop after each one, and maybe if you have questions, we can do them right there instead of trying to save stuff to the end. So the purpose is to be short and sharp, and I'll try to do that. However, having put the words 2 freaks and a conundrum on the screen, I have to go to the next slide, which shows my 3 graduate students at the moment. And you have to guess who is the conundrum and who are the 2 freaks in here. So here you've got Manto Hu, Ariel Grakowski, and Dave Oleski. These 2 have given talks here at Gemini in the last year or 2, probably because of CE. You have yet to have the pleasure of a talk from Dave Oleski, but I assume that will happen eventually. I hope so. Okay, so 2 freaks and a conundrum. All right. First one. So each one I'll give you a little bit of a background because I assume most people are not solar system specialists, and then I'll just tell you what I've done, what we've done. So this is an object called P5. So about 12 years ago, and I'll put down some papers. I know you don't care, but I put down. I'm one of those people who still believes that papers are important. Even in the 21st century, I kind of care about writing the papers. It does matter. I know it doesn't matter that much to a lot of people anymore, but I think it matters. It's kind of a record, and then you can move on. 12 years ago, with my then graduate student, Henry Shea, who's still over there in Honolulu, we identified this new class of body in the solar system. We called them, at the time, main belt comets, but now we call them active asteroids. So they're objects which, by their dynamics, are clearly asteroids. They're mostly in the main belt between Mars and Jupiter. They have Tisserand parameters bigger than 3, if that means anything to you. And in fact, even if it doesn't mean anything to you, it's still, it's true. They have Tisserand parameters bigger than 3. But they don't look like asteroids. So an asteroid is a rock, right? And it's an inert thing. It's orbiting the sun. These are asteroids that look like comets. They're throwing out mass. And so the basic question is, what's going on? Why are they ejecting material? So in the last decade or so, we've identified a number of different reasons why an asteroid might do that. And They include such things as impacts. You have a collision between two asteroids can blow out debris, and the debris is picked up by radiation pressure and makes a tail. It looks like a comet for a little while, and then it all blows away. There is evidence for sublimation in these bodies. So we used to think the asteroids could not possibly contain ice because they're too hot. But we have found a bunch of objects in the asteroid belt which apparently do contain ice. They sublimate, and they do it periodically. They come near the sun, produce dust, make a tail, go away from the sun, it stops. And they've done that several times. So we have, a little bit more than a handful of objects like that out of a total sample now of about 20 or 22 of these objects. And then there are still others that are just strange. And so this is one of the strange ones. And it's got a horrible name. Everything in the solar system has a horrible name. So we'll just call it P5 to keep that simple. So P5 is special because of its appearance. And its appearance is special because it's unique. So I don't really need that. But, this is an object, it's an asteroid at the inner edge of the asteroid belt. Similar bodies nearby are of a highly metamorphosed type. They've been up at temperatures like 800 Kelvin, maybe 900 Kelvin. They've been cooked. So water ice should not be present in these bodies. So I don't think water ice is responsible for this. It hasn't been subject to a recent impact. This dust has been coming out for a long time, over many, many, many months. But the most special feature is it has multiple tails. So there's a tail here, here, here. So there's 6 on this picture. There are 3 more that appeared after this picture was taken. This is a Space Telescope picture. So 9 events over 9 months. Each one is like 100 tons of dust that comes off this thing. At first, I had trouble seeing this. When I finally figured out what this thing is, what it looks like, I then have trouble understanding what could be happening with this object. It turns out that each tail corresponds to a discrete ejection of dust. So it's not like I'm standing here with a handgun shooting out bullets. I shouldn't probably do that in the modern era. But I'm not rotating and shooting out bullets that go out in a straight line. This corresponds to an ejection of dust. The dust comes out at nearly 0 velocity from the thing, and then is picked up by radiation pressure and blown back into a tail. And the position angle of the tail is a measure of the time when the dust was ejected from the body. So this corresponds to a series of discrete ejections from this body, 9 of them spread over 9 months, not periodic, irregular intervals from a week or so to more than a month. As I say, about 100 tons. And that is not like anything else in the solar system. Comets don't do that. Comets, which are sublimation driven, they just belch out material and it comes out, it doesn't come out in discrete pulses like that. So it's a very, very strange object. It's a rock, it's hot, it's not icy, and yet it's ejecting dust in spurts. What could that be? So the idea that floated up, the only one that seemed to fit, was basically avalanche. So I think this body, the first model in the first of those papers, the first model is, this is a body that's been spun up by torques from solar radiation. And that's a known process. The timescale is right. It's a small body. It's a couple hundred meters across. And so on timescales of less than 1 million years, solar radiation can spin it up. And it's spun up close to the centripetal limit. And so material on the surface that starts near the pole, for example, can roll down towards the equator because of centripetal effects. When it gets to the equator, it can fall off. And as soon as it falls off, it's picked up by solar radiation pressure and off it goes. So it makes a tail, discrete tail like that. So the physical picture in my mind was, imagine a tray full of sand and you tip up the tray. It's flat, a flat tray of sand. You tip it up like that. And just before the whole damn thing slides off, you look at the surface and you see little spots on the surface are locally unstable. So you have a micro avalanche here and a little one there. So each micro avalanche corresponds to a tail ejected from this body. That was the picture. Okay, so that's a novel idea. We haven't seen anything like that in the solar system so far. Tail ejection dates are here. So you can see they're spread over several hundred days. And my observation dates with HST, for the most part, are these empty squares here. So I have a bunch of measurements of this thing just to see what's going on. basically over here, it's ejecting material. Over here, it stopped. So after, this is distance from the sun. After perihelion, it basically stopped ejecting stuff. Okay. What you can see is that it's a little bit brighter. So this is a model of how bright the thing would be if it didn't eject dust. It's a little bit brighter over here before perihelion than afterwards. So these red points basically fit on the model line, and the blue points tend to be a little bit above, but not by much, a few tenths, maybe half a magnitude at the most. So slightly brighter, consistent with cross-section added by the ejection of dust from this body. And the same thing is shown here. This is absolute magnitude. It's the magnitude corrected for the inverse square law, basically. And you can see it's brighter here, smaller numbers at the top, than it is down here. And there's some scatter, which is real, and that's probably, I thought, because this is a rotating body. Rotation is important if landsliding is the explanation for this mass loss. So the next test, and the most recent of these papers, will be to actually look to measure the light curve of the nucleus, because if it's a rotating thing, we should be able to see the cross-section varying as it rotates. And it should have some kind of a sinusoidal light curve variation, and it should be fast. And we know from the asteroids that there's this critical period, like 2.5 hours, below which bodies are rotationally unstable. So my expectation was, do a light curve of this thing, no problem. HST, a bit of a problem, but we'll be able to see a rapid light curve variation. And so I took that data, and the data came out like this. And that's a bit of a problem, because here now is more than 5 hours. It's 14 hours up to 20, so 6-hour window on this plot. And we see a light curve that does not repeat, even within 5.5 hours of data, 5.4 hours of data. So the period of whatever it is cannot be 2 hours. It must be at least 5.4 hours, since it hasn't yet repeated. Conceivably, you know, if we kept going, this piece would fit onto here, so it could be 5.5, 6 hours period, but it's not 2. And so that, at first blush, appears to blow out of the water the possibility that this is a centripetally driven mass loss coming from this body. So my wonderful hand-wavy model, not supported by the data. So then the question is, what is this? Well, if you look at this minimum in the scattered light, it's a 30% deep minimum with roughly a V shape. And this is the kind of thing you see in an eclipsing binary. So if you have a double asteroid, one component goes in front of or behind the other one, the light shows this kind of variation. Okay, so this corresponds to a transit of one thing in front of another thing in a binary where the separation is probably not very big. So on that assumption, I figured out a few things. So we know how big the object is. We know how long it takes to go from there to there, so we can estimate the Keplerian velocity of the body as it goes around. If we know how big the thing is and we know the Keplerian velocity, we can estimate the distance to the secondary body. So we can characterize the parameters of this binary body if it is a binary body. And it works out to give us fairly reasonable numbers, as I'll summarize in just a moment. We do see short-term variations. So these are individual windows of about 45 minutes from HST, where the brightness is changing. The error bars are a little bit bigger than the dot, are very, very small. We do see variation on very short timescales, but I don't have any data good enough to show any periodicity to these short-term variations. We just see this large-scale structure on this 5-hour observing window we have with HST. So there's quite a lot of stuff in the light curve, but it does not fall over backwards trying to help me with this idea that it's avalanching material coming off this body. I also searched for escaping secondary companions from this thing, and there are none, down to about 28 mag, so that's about a 10-meter body, so roughly the size of this room. So there's no bodies as big as this room floating near or escaping from this asteroid. So the idea there, why would you look for that? The idea is that if it's a rotational effect, maybe it's actually breaking up and it's ejected some big pieces, but no evidence for that either. All right, so there are the parameters of the binary. The big one is about 180 meters in radius. The small one, the secondary, is about 100. So the size ratio is 0.5, 0.6. The light curve period is 5.4 hours or bigger. My best guess for the orbital period is a big fraction of a day, 0.8 of a day, something like that. And the ratio of the separation of the components to the size of the primary is about 4. Okay, so those are the parameters of this system, if it is indeed a binary. The question is, though, how does this fit at all with the original idea that this is a body on which material is landsliding off the surface because of rapid rotation? And the answer is muffins, as you know. So I had one for breakfast. They do indeed look like this. If you have a muffin-shaped body and it's rotating around this axis, it's approximately symmetric. So the light curve you would get from rotating this muffin is due to the chocolate bits, not really due to the overall shape of the muffin. So you would have a small amplitude light curve, not a big one. So my thought is that, in fact, we do have rotational instability, but for one or perhaps both of the components. Okay, and the rotational instability is on a body which is roughly azimuthally symmetric, and so it gives a small amplitude light curve that we have not yet successfully detected. Whereas the basic structure of the light curve is due to this mutual event between the two bodies, one passing in front of the other. And you could say, well, what are the chances that this thing will be shaped like a muffin? And the chances are very, very good. And we know that. Well, here's one to which the Japanese have sent a spacecraft, a very excellent mission called Hayabusa 2. It's gone to this thing called Ryugu. And it's shaped like a muffin. And why is it shaped like a muffin? It's because material is avalanched down from the polar regions towards the equator and then fallen off. So that all hangs together. So I think that one or both of the components of this body probably are like that. They have this kind of shape. So I think this thing, the basic idea, tipping up the tray of sand, I think that was a good idea, but the complexity is it's occurring in a binary. Other asteroids, close binary asteroids in the main belt, are thought to form by rotational breakup. And so I plotted this object on a couple of graphs to see how it compares. Here's the size of the primary, 100 meters, 1 kilometer, 10 kilometers. Here's the ratio of the sizes of the secondary to the primary. And the red dot is basically in the cluster. It's a bit to the left because it's very small compared to most of them because of the dust, basically. If it hadn't ejected the dust, we would not have discovered this body. It's too small, it's too faint. No survey would have picked it up. So it's kind of raising a flag. Hey, look at me, I'm throwing out dust. And that's why it's over to the left on this plot, and this one too. This one shows the ratio of the orbit size to the primary diameter size. Here's a line here for coming inside the Roche limit, where the primary can shear apart the secondary. They all kind of avoid that. And this one does too. So it would not be an exceptional body compared to other binary asteroids, if that indeed is what it is. So the difference is, since we have all these others, who cares? The difference is it's happening now. So the dust release is almost certainly related to or a consequence of the formation of this binary body. So we have a chance to study this process of splitting, binary formation, and possibly secondary ejection in real time, something that we could never do before. So a quick summary, they're all supposed to be tiny micro talks. A quick summary is that this episodic landsliding, which has now been given the fancy name mass shedding. Mass shedding, I think, is still the best model. There is no other model. So by default, it's the best model. There is no other model for this thing. I think it's still plausible, subject to this complication that it's in a binary. It's probably still ongoing, so we may still see some more activity in this thing in the future. And it's part of a family. Here's another one that we imaged with Space Telescope. This is also an asteroid, which actually broke itself to pieces because of this rotational torque that took it up to such a rapid rotation. Cohesive forces couldn't hold it together. So we're starting to see the beginnings of the continuum of rotational breakups in the asteroid belt. We'll probably be able to use these things in the future to understand how that breakup occurs. Okay, any questions about that first talk?
Yeah, two. So have you seen any other ejection events from P5 except the one at 2013?
No.
And
It just did nine events. Probably did some more before it was discovered, but it did the 9 events, and that's it. And it has not done it since.
and if it's so symmetric, how does it spin up? First of all,
Well, okay. So the thing we're talking about is called York torque. York is an acronym for this radiation torque. The origin of that indeed relies on asymmetry. It can be asymmetry that's very, very small, and it can actually change sign as the surface changes shape and so on. So the connection between the geometry of the body and the York torque is actually very complicated and very messy. As long as there's some asymmetry, it's going to work. The body is so small that the York torque can do this job in a time that's short compared to the likely age of this body. So this is probably created by an impact in the last, let me see, in the last 50 million years, something like that. So it will not survive, for another 50 million years because it'll be smashed to pieces. So the York time scale is probably 1% of that. And so even a small torque on such a small body is going to do the number. So it wouldn't be at all surprising for York to act on this. And the only way to stop the York torque, the only natural limit is the breakup limit. It just goes faster and faster until it can't take it anymore. Yeah.
So what's that asteroid that looks like a peanut? It's very asymmetric. Somebody was, I think they sent a probe out to it like 2 years ago.
Yeah, there are a bunch of asteroids like that.
Oh, well, okay.
And comets.
That makes my point in that it sounds like it's kind of a prototype version of this binary, and that's something that would get spun up, I would think, and would turn into a binary someday, maybe.
Yeah. And the question is, how did that peanut come to be? Were those peanuts individually, were they individual nuts?
I hadn't thought that far back yet.
Separate space flying nuts that came together to make a peanut? I think that's quite likely. So actually the complexity of the asteroids is staggering. So they've gone from being, oh, that's a boring little rock, to, my God, that's a complicated dynamical system in the last few years. So in fact, that process of a York torque spin-up of a small body can lead to the ejection of mass and to bifurcation, and like in the one at the bottom, complete splitting of the object if it happens too fast. But the binaries themselves are not necessarily stable because there are torques, so that the central body has a slightly aspherical shape, and so it can exert torques on the satellite. There's impacts into the satellite from more debris coming out. Coefficient of restitution is 0.8 or something. So there's energy dissipation in the system. The secondary can be launched and lost after being in orbit for years, or it can recoalesce after years, according to numerical simulations. So the peanut objects like that could have formed from a binary which reassembled in itself. It's too early to say what's happening in any given case, but we now see this broad spectrum of behaviors for asteroids. Yeah. So I think this is kind of a good angle to look at that, because we could use data instead of just relying on models. Everybody loves models, but in the end, it's just a model. Yeah.
So LSST is going to find something like 5 million asteroids that we'll be monitoring with hundreds of observations. So things like this will pop up. Is there anything that would be useful or to study this better? Because we'll be getting photometry, basically, we'll get the alert stream basically from LSST live right after each observation. So is there a good way to sort of help probe more about sort of asteroids like this? Is it follow-up or just getting more examples?
The great thing about LSST is just keep, hopefully, if it works, just keep going, right? So it will do the light curves that we struggle to do. It won't be as good as HST, it won't go as deep, or all the rest of it, but it will give us very good time coverage of the light curve. And that's what we need here to make further progress. So I want to know, is that really the case that was an eclipsing binary? And is there, in fact, evidence for a short-term modulation from one component? Maybe we'll get lucky with some similar bodies, brighter bodies, closer bodies from LSST data. So that will be extremely informative. And then just monitoring this over time, your question, does it eject dust, in different years or different orbits? that will be very interesting as well. So the models at the present time are massively under constraint. And so they don't really tell us useful things, but they point at many interesting things, some of which could be true. I think the new data from LSST will be able to narrow down this broad picture that the models are giving us. Yeah, so it's going to revolutionize this because it's time domain astronomy, and that's what LSST is for. All right, so I go on. Don't want to take too long because we've got 3 talks. So again, the point of this is just to talk about fun stuff, right? Okay, so you probably know that the standard model of comets was made by this guy, Fred Whipple, who wrote this paper in 1950 saying, yeah, most of what we know about comets can be explained by assuming that they're dirty snowballs. So the dirty snowball comes in close to the sun, ice in the snowball sublimates, and drag forces from gas blow out pieces of dust. It makes the tail and coma and so on. If that were all there is to it, there would be comet activity only inside the orbit of Jupiter, because water is not that volatile than ice. And it's only warm enough to sublimate appreciably inside the orbit of Jupiter. Okay, outside Jupiter, the comets should be dead. Now, we've known for 100 years that you see comets beyond Jupiter, which are active. And that's always been a bit of a puzzle, but in fact, for most of them, it's not a puzzle. For most of them, they are comets which have been through perihelion and which have picked up the heat from the sun at perihelion, and which are then carrying that heat, which conducts slowly into the interior. It takes a year to go that far because the diffusivity is so low. And so the activity is driven by heat obtained in perihelion and conducted into the interior, where it activates some volatile pocket or something, and you have a little explosion. So for most of the comets which are active beyond Jupiter, it's no big deal, actually, although some people think it is, it's not. But there are some comets, very few in number, probably 3, which are observed to be active on the inbound part of their orbit, far away from the sun, way outside the orbit of Jupiter. Okay, so they're a real puzzle, because you can't say, oh, it's heat from perihelion that's just slowly propagating through the interior, because perihelion was just so long ago, that's not feasible. So the current best case for that is this thing, 2017 K2, which I will just very briefly talk about. That was the intro part. All right, oh, there's a picture showing the orbit. It's coming in roughly perpendicular to the plane of the solar system. It's going to come into about 1.7 AU, a little bit beyond the orbit of Mars. Won't get there until 2023. Its current eccentricity is slightly bigger than 1. So it's on a hyperbolic orbit. That's because of planet perturbations. If you take those out, you find that it's probably been through the solar system before, and it came through the last time with an eccentricity of 0.99993 or something like that. So it's bound to the solar system. It's not one of these interstellar things. It's from the Oort cloud. The aphelion is out there at 50,000, 40,000 AU. The orbit period is millions of years. So it hasn't been near the sun for millions of years, and yet it's active. It was discovered at 16 AU, and I'll skip over that one. It looks like that. So there's my space telescope picture of that thing from the summer of last year. So what does that look like? Well, it's kind of like some kind of horrific galaxy or a globular cluster where you can't resolve the stars or something like that. It's kind of a weird thing. It doesn't have a tail. It's very, very spherically symmetric. This is stuff in the background. That's it. A very strange looking comet. But the main thing is it's really far away from the sun. So it's what? If there was a tail, which way would it be in there? Well, it depends on what the tail is caused by. If it's caused, I'll show you in a different diagram, but if it's caused by radiation pressure, it will be in the anti-solar direction. If it's a tail made of big particles, they tend to stick close to the orbital plane, so it would be in the direction of the projected orbit plane. So there's a range of directions where you could physically explain the tail, but we just don't see a tail, which turns out to be very important. So we went back through archival data and found it in pictures from the fabulous CFHT when it was at 24 AUs from the sun, 24 AUs. So beyond Uranus, almost out to the Kuiper belt. And that's it. We know that's it because it moves and so on. It's not just an image defect. So it's been active at ridiculously low temperatures. 50 Kelvin, something like that. It was throwing out stuff. Water can't do that. The backup mechanism that people have suggested for comet activity is crystallization. So if you have amorphous ice in a comet, it can crystallize. When it crystallizes, it releases energy, it's exothermic. And it also releases gases that were stuck into the amorphous structure. And when it settles into this hexagonal ice molecular arrangement, the captured gases are excluded. So you get a big burst of gas, and the big burst of gas is powered also by this exothermic release of energy occurring upon crystallization. That can happen at about 10 AU, the orbit of Saturn. But this thing is way too cold, even for crystallization. So mechanism number one fails, sublimation, not going to work. And mechanism two, crystallization, fails, not going to work. So what's going on with this body? Yeah, the directions are shown here. This is the anti-solar direction, to answer your question. This is the projected orbit, since it's coming in perpendicular to the solar system. So, bizarre. So I got more HST time in the last year. So these are the images that I've been collecting. There's a little asymmetry, but there's nothing in any of the expected directions for a tail. It's basically a very, very circularly symmetric coma. It's about as big as Jupiter, a little bit bigger than Jupiter in the region that's shown in these pictures. So it's a big thing, and it's getting bigger. The surface brightness profile looks like that. Out there, forget it. So out here, we're very sensitive to uncertainties in the way that I subtract the sky background. So ignore that part. In there, we're sensitive to convolution with the PSF of the Space Telescope. So forget that part. But in here, we can trust it. We're not affected by PSF or by sky subtraction errors. And the slope is -1. It's very close to -1. -1.01 plus or minus 0.01. It's -1. And that's highly significant because that means that the mass loss from this body is occurring in steady state. And the reason is, if you have, by equation of continuity, if you're just belching out material into the interplanetary medium from some comet, the density falls off as 1 over r squared as you go out into larger and larger volumes. But when you look through the coma, which is optically thin all the way through, you basically gain back. You do the integral of 1 over r squared, you get 1 over r. That's exactly what we see. So it's a steady state coma. So it immediately rules out impulsive ejection. There's no explosion that suddenly gave rise to this comet activity. It's a steady thing. It's grown probably very slowly from 26 AU to the present distance. It's down to about 14 AU. But it's a long-term ejection of material into the comet. Now, one other thing that you can say just by looking at this picture and looking at the circularity of the isophotes and the absence of a tail is that radiation pressure is not important in pushing these particles around. Why would that be? Well, radiation pressure is not very important in pushing CE around because she's big compared to the wavelength of light, as are we all. So radiation pressure is very effective on small particles and not big ones. So the absence of a tail produced by radiation pressure is an indication that these particles are large. So I did my usual back of the envelope thing, and I got 0.5 millimeter or something like that. And then we've modeled this with a full power model, and we get the same answer. So the particles are a big fraction of a millimeter, not smaller. Smaller ones would make a tail. That's pretty weird too, because you would think far away from the sun where the gas flow is relatively weak, you would only be able to lift out the small particles. But in fact, the comet is lifting out the big particles. Now, I also looked at the photometry. So I divided the coma up into a bunch of rings. There's a little one in the center, and they just get bigger. And I plotted those rings as a function of time for the last year or so. And you can see all of these lines have a positive slope. And you can also see that if you project them over there, they come down to this axis. This is 0 cross-section or 0 brightness. They're all going to converge like over there, 20 feet on the other side of this wall. The cross-section of this thing was 0. So that's how I know that the activity started when it was at 26 AU from the sun. It was observed at 23, but it actually began at 26. And it's been brightening slowly ever since. approximately in steady state. So that's the summary of those fits. The fits basically tell us the activity started in 2012. The first CFHD archival detection is about a year later, something like that. So that hangs together. But it's just weird that a comet should be active so far away from the sun. So what could be driving this stuff? It's not water, it could be some other volatile. Right? So here's water, here's distance from the sun. Here's how strongly a material sublimates. Water just dies, forget it. CO2, unless it's right at the subsolar point, also just dies. But CO2 at the subsolar point where the temperature is maximum, noonday sun makes it really hot. That could just about drive activity in the region where we observe the comet. And CO, the supervolatiles, carbon monoxide, diatomic nitrogen, things like that, are volatile enough that they can power the activity out where we see the activity in HST data and discovery, the initiation of activity out there at 26 AU and so on. So maybe it's just super volatile CO, which wouldn't be that surprising because it's been basically in the Oort cloud where the temperature is like 7, 8 Kelvin or something for the last few million years. Maybe the CO is just there for that reason. And that sounds great until you think about dust. So I'm looking for some dust. Oh, I found some dust. Here you go. So that dust is sticking to my finger because it's small, right? And so you can actually work out the cohesive strength by looking at the biggest particle that can successfully stick to your finger. On your finger, it's more sticky because of water. So water makes a good bonding agent. But the stickiness of particles has been measured and calculated by a lot of people over time, because a lot of people care about dust for all sorts of technological reasons. So here's the strength of the lunar regolith. It's a few hundred to 1,000 newtons per square meter. Here's the strength of that active asteroid that I showed you a picture of. That's broken up into pieces. It's roughly 100 newtons per square meter, pascals, some people say. Here's the effective strength of Shoemaker-Levy 9, this comet that was sheared apart by the gravity of Jupiter in 1994. Here are some models, and here's the gas pressure generated by sublimation of CO2 and CO. So the more volatile one, CO, and there's almost nothing more volatile that we would find in a comet. The more volatile material produces a gas pressure that is orders of magnitude too small to overcome the cohesive strength of dusty material. What about that? So basically, we can eject material from a comet, and the standard model is you consider the drag force against the weight of the particle pulling down to the nucleus. But for most comets, for most particles, the cohesive force of the material is far larger than the weight force. And so it actually determines what can get out. And so this comet is an impossible comet. It cannot possibly be active. But it is. So I'm just grappling with that now. Any questions about that one? Any answers? Yeah.
Sorry,
Yeah,
what sort of particles do you assume? Do you assume fluffy?
I presume they're fluffy, but because people say comet dust is fluffy, but I have no idea, right? So they're on the order of a millimeter size. I know that from the absence of radiation pressure deflection. That's about all I know.
So I assume and then when the tail appears, that'll tell you particle size.
I started asking for HST time. First of all, just have a look and see what it's like at high resolution, and the hope was to isolate the nucleus. And it turns out we only get a constraint on the nucleus. It's not bigger than 5 to 9 kilometers, something like that. We would see a separate blip in the center that we don't see. So it's not a monster nucleus, as many people were saying it must be. Then I thought, well, hey, this is a really cool thing. This comet is just kind of amazing. It's active at such a large distance. I need to look again. And so I wrote another proposal to get more time to monitor the development. And the big surprise to me is that not a lot happened. You know, it kept those circular isophotes. It got a little bit brighter, came closer, but not a lot has happened to the comet. So it's really a kind of a magnificent object coming into the solar system, as I say, bigger than Jupiter, immune to radiation pressure distortion so far. And it's kind of challenging me to measure things about it.
There should be a tail eventually.
Eventually, there should be a tail, yeah, given enough time. And depending on what happens with this cohesion bottleneck, eventually smaller particles should get up. So I'm guessing, the reason we don't see small particles at all is that they're stuck on the surface. The small ones, the cohesive force between spheres, for example, is actually inversely proportional to the radius of the particle. So the smaller the particle, the stronger the cohesion, which is why you have small particles that are sticky, stick on your fingers, and not, chairs and things like that. So it's reasonable to suppose that the absence of tiny particles is because they are held back by the cohesion barrier. The question is, how is the cohesion overcome, even from these millimeter-sized particles? Because that previous plot shows that it's many orders of magnitude. I mean, to go, regolith is very well determined, but this thing is a comet, this thing, there are many, many powers of 10 that need to be overcome somehow. So I'm trying to understand that. I have a couple of ideas. One idea is thermal fracture. So thermal fracture sounds stupid because this thing is at 60 Kelvin now, something like that. But the point is the temperature is still changing. Day-night variation is causing the temperature to go up and down. And if you estimate the thermally induced stress due to expansion for ice at those temperatures, you can indeed crack ice. So if you crack the ice, you instantaneously pop off particles, and then they don't care about cohesion. Once they're popped off, off they go, and they're free that way. That's one possibility. The other one is related to what's called the horizon glow on the moon. Are you familiar with that thing? Surveyor, 1966. So Surveyor's spacecraft was sent to the moon to basically check out the surface properties to make sure it's safe for people to go in the Apollo missions. So they landed these three-legged things, and they took pictures and did measurements with that little scraper and so on. They took pictures towards the rising or setting sun, I forget which, showing a band of light over the horizon, just like you would see at twilight on the Earth. Now, on the Earth, no big deal. It's scattering by the atmosphere, but the moon doesn't have an atmosphere, so that's not a plausible cause. And instead, the interpretation was there are particles 5 microns across, 10 microns across, somehow above the surface of the moon. And there's other arguments why that is the case. So those particles must also overcome this cohesion bottleneck. Somehow they are also snapped off the surface. And I suppose it could be a thermal expansion thing, but the belief is that it's an electrostatic charging effect. So the surface of the moon is a dielectric. You put a dielectric in sunlight, photons ionize it, the electrons go away, and the thing gets a positive charge. That charge is not that big. It's only about 5 volts because the UV photons that do it are about 5 eV, something like that. So that's probably not strong enough to launch particles, but people are looking at ways to amplify the electric field that you would get from that kind of potential difference in a particulate medium. So there's a new thing called supercharging of a planetary surface. And supercharging may be what drives particles off the surface of the moon. And in the case of a comet, where the gravity is so small, maybe pops them right off the comet into space. Yeah.
Do you have an estimate of mass and its orbit? How close is it going to come into the sun?
Yeah, I forgot to mention the mass. The mass in the coma, like in the last observation, which was a few months ago, was 4, in these millimeter particles, was 4 times 10 to the 10 kilograms. The average mass production rate, since these have all been produced since 2012, is 200 kilograms per second, which is extraordinarily large for a comet out there, which should be totally inactive. So it's belching out a lot of stuff. That mass is small compared to the mass of the nucleus. If it's a 5-kilometer sphere, it's, I don't know what that is, 10 to the 17 kilograms or something. Yeah. So it's a small fraction of the total mass, but it's still a large mass and a large mass flux coming off the surface. So I think it's not totally clear that this electrostatic supercharging can do that, but it might be able to do that.
So this is going to be a solar grazing.
It comes, as I say, it comes into about 1.7. So Mars is at 1.6. So perihelion is a little bit outside Mars.
Okay.
Yeah. And of course, whenever a comet is found far away, these people come out of the woodwork and say, oh, it's going to be the comet of the century. It's going to be awesome. And that's because everybody, for some reason, fits really steep power laws to comets, no matter what. Like, it doesn't have to be any evidence or reason to do that. It just fit a really steep power law. So it's going to be incredible. It's going to be like daylight when it gets to perihelion. There's no evidence for that whatsoever. And in fact, I don't even know if it will get brighter or fainter, because if these grains in the coma are icy, as they probably are, they're stable out there. When they come close to the orbit of Jupiter, they'll all disappear. And it could get fainter, in fact, not brighter.
But you could just be patient and wait for this to get closer.
I'm a very patient person, and I'm waiting. But I want to wait, I want to squeeze everything out before it comes in. The thing is, this is in a totally unobserved realm, so we don't have physically constraining measurements of anything out there. This is going to give us the whole lot. It's going to cross the crystallization zone. When if there's amorphous ice, we don't even know if there is. But if there's amorphous ice, we'll see the effects of crystallization. Then it's going to come into the sublimation zone. We'll see the effect of the sublimation on dust and everything else. And then eventually the nucleus should turn on like a classical comet nucleus and start sublimating water ice from the nucleus. So we'll get to see, I think, the full range of comet behaviors for the first time. Yeah.
Yeah, I'm just wondering if we don't really understand ice physics very well, because the same problem comes up with Sharon, right? Nobody expected it to be as ripped apart and have a big gash on it. We all expected it to be the, source for creating, we'd measure the craters in Sharon and be done, right?
Yep.
And so clearly Pluto Sharon in that binary are able to elicit much more tidal heating than anyone would have predicted.
Yep.
Is it maybe that we don't understand the crystalline amorphous transition as well as we think we do?
Maybe, yeah, but the satellite is still very big compared to this thing.
Right.
It's still a few kilometers across. It's hard to see how any kind of internal heating would ever be important in a body so small, So I think it's in a different league where it's almost certainly really cold. And it does have very low gravity, so it is sensitive to actual loss of mass. Stuff will just fall off the surface, provided it overcomes the cohesion bound. So I agree, the ice is a mysterious substance. Okay, I'll do the last one quickly. So I need a background as well. So you're familiar with the Trojans, perhaps. So we've known for a long time, here's Jupiter. We've known for a long time, and here's the asteroid belt, that Jupiter retains two families of Trojan asteroids, ahead of it by 60 degrees and behind it by 60 degrees in its orbit. So those are the Trojan asteroids. First one was discovered in 1901 in Berlin. And I gave a talk recently in Berlin, and I remembered the fact that the first one was discovered in Berlin, in my talk in Berlin, which freaked me out. I almost lost control of the talk because I had this strange memory from somewhere. Anyway, so they're about 100 years old. There are many of them now. We know of 7,000 of these objects. But there are very, very many more. There are probably as many Trojan asteroids as there are asteroids in the main belt. They're just harder to see because they're a bit further away and a bit fainter. So who cares? Well, there are a bunch of questions. The main question is, how did Jupiter get them? How did it capture them? They're clearly captured somehow. And there are different ideas about that. There have always been a range of ideas, and they go from the first extreme, which is, well, there are local captures. So these are asteroids that were nearby at the time when Jupiter grew in mass. Its gravity went up, and it basically was able to stabilize or semi-stabilize the Trojan asteroids that do that kind of thing relative to the L4 and L5 points into these vibrating clouds. So local capture actually is preferred because to be captured, you need a very slow relative velocity to have any chance of being captured into this region. If you put your foot on one of these things and gave it a good kick, you could kick it out of the Trojan swarm. So they're not very stable. So they're a very delicate system of bodies. So that's one extreme. Local capture actually makes the most sense. The planetary science community, in its infinite wisdom, has decided, oh, that probably didn't happen, and instead they're captured from the Kuiper belt. So the big thing in the last 10 years is everything is from the Kuiper Belt. Kuiper Belt went through this unstable phase. It blew out all this material. A whole bunch was lost to the interstellar medium. A lot of it went in and hit the sun. And then some more, about 1 in a million particles, was the irregular satellite around the planet. And so there are people with computer programs, black box programs, where they can show that, well, that could have happened. So that's become the accepted reality. These are captured Kuiper Belt objects. So I thought, well, if that's the case, there should be an observable consequence. The trouble with all these models is they don't really make strong predictions about anything, so they're very hard to test. But there is a prediction that's made by that idea that, you know, at the dumbest level, the color distribution of the Trojans should be like the color distribution of the bodies in the Kuiper Belt that were ejected. So that's called the hot population, the dynamically excited objects that could be kicked out. So we've known actually ever since the first color measurements were done in the Kuiper Belt in mid-1990s that that's not true. We know that the Jupiter Trojans do not have the same color distribution as bodies in the Kuiper Belt. And the main difference is that the Kuiper Belt has this ultra-red material and the Trojans don't. We don't know what this ultra-red material is. People, including me, think it's probably organic material. It's probably irradiated in some way. In a sense, for this argument, we don't care. We're just doing a comparative study. But the expectation that the Trojans should have the same color as their parent bodies is not met by the data. So various people, including me, believe that, well, you know, maybe that's because the surfaces of these bodies, if they came from the Kuiper Belt, were modified by the inward movement. They came closer to the sun, they got hotter. In the Kuiper Belt, they're 40 or 50 Kelvin. At Jupiter, they're 120 or something. And then that's going to enable chemistry in the surface. It's going to mobilize volatiles. Maybe you can sublimate some stuff. You're going to change the body. So perhaps that ultra-red material is destroyed somehow, thermodynamically destroyed, or just buried under fallback debris. It's changed. But now we know that Neptune also has a bunch of Trojans, presumably captured from the same place in the same way. And so we can do that same test on the Neptune Trojans. And the big deal with the Neptune Trojans is that they have not come closer to the sun. Neptune is about the same distance as the Kuiper Belt, so the temperature is about the same. It's 40, 50 Kelvin, something like that. They never got hot, so they're not subject to any thermal modification process. So they should have the same color distribution as the parent bodies in the Kuiper Belt. Oh yeah, here's a summary thing showing the colors of bodies, two optical colors. So these red things are different bits of the Kuiper Belt, and the Trojans of Jupiter and Neptune are down here together, but far away from the stuff in the Kuiper Belt. So and here's the sun down here. So they're redder than the sun, but not nearly as red as these things in the Kuiper Belt. Again, primarily because of the absence of this ultra-red material. So as histograms, it looks like that. So here are the Neptune Trojans, Jupiter Trojans, and then various so-called hot components of the Kuiper Belt. And here's the cold classical, the dynamically cold, undisturbed, maybe primordial component of the Kuiper Belt down here. Ultra-red is bigger than about 1.6, so there's kind of a line going up there like that. And you can see all these populations have a bunch of ultra-red objects, but when you get down to the Jupiter Trojans and the Neptune Trojans, the ultra-red material is depleted, severely depleted. So what's the difference between these histograms and these histograms? The source population histograms, not this one, source population and the Trojans. By eye, looks like it's different to me, but nobody likes that. If you write a paper and say, well, by eye it looks different, you got to back that up with some statistical test or something. So the KS test, and then a variant on the KS test called the Anderson-Darling test, both show that this is significant at about the 3-point-something sigma level. So it's quite unlikely that we could, just by chance, take out only the blue objects from the Kuiper Belt. You know, just doesn't seem like it's going to happen.
So Dave, you include Edward Lynn's ultra-red Neptune Trojan. Is that the one object there? So it's one. The deal is 1 out of 16 instead of
1 out of 3.
So does it matter though with the observational bias is that one of the Neptune Trojan clouds is in the galactic plane? And so we're not getting, I think it's the
It hurts with the size of the sample, yeah.
right.
Yeah. But I think unless one cloud is different color from the other, which doesn't
should
fit
get
into anybody's model, that would be an even more interesting discovery. if
Because
that were the case.
Edward's object is, I think, high inclination. And so there's a difference in inclination between that and the usual one.
Uh-huh.
Is that, have you looked
I
at
just
that in terms
I
of
just
physics?
observed all the Trojans I could observe, and I collected a bunch from the
Okay.
literature done by Scott Shepard and somebody else. I just got everything I could. Yeah. So you can argue there are different ways out. Actually, I summarized the possible ways out. Oh yeah, here's the same thing as cumulative histograms. The primordial bodies, the cold classicals are over here at one extreme. The Trojans are over here, the blue and the green ones, and then the hot population is over here, distinct from either extreme. So here are the solutions that I can think of. First of all, maybe we'll add more data and this effect will go away. 3.2 sigma, stranger things have happened, right? Could happen. So the first idea is just get more observing, get more data, find more objects that we can observe because they're actually very faint and hard to observe. And perhaps this difference will go away. We'll suddenly find a bunch of ultra-red Trojans. Possible, but the statistics tells you that's not likely, right? That's a 3 sigma thing, if that's going to happen. But it could happen. I'm open-minded. Or there might be some other process that modifies the colors of Trojans at Neptune. So maybe the Trojans of Jupiter are thermally modified because they became warm by approaching the sun. The Neptune Trojans never did, but maybe there's some other thing, like some collisional process that could reset the surface colors on the Neptune Trojans and make them blue. Magic. Could happen. Magic can happen. Or maybe the idea is just wrong. Maybe they're just not captured from the Kuiper belt at all. I think that's very plausible as well. So I don't know what's going to happen. I don't really have a preferred answer to this. I just think that it's interesting that when you give this model a chance to succeed, by giving you the right color distribution, it doesn't. So nature doesn't want to play ball, basically. Okay, so I think that's pretty much all. Yeah. Any questions about that one? Just that means no questions. What does that mean? It means get out.
I always got questions. I mean, the Muse model does a lot, but it's good not to throw it out. I mean, it does explain the regular satellites of the giant comets. Why can't there just be another ice line? So why can't we just say that intermediately there's another ice line?
So what we see in the centaurs is very informative. So if you look at the color, centaurs are recently escaped Kuiper belt objects that are being scattered by the giant planets. So the last 10 million, 100 million years. When you look at the centaurs, they were actually plotted. They do include a mix of the ultra-red and the blue. So the centaurs are consistent with the dynamical picture, which is that they recently left the Kuiper belt, the hot population of the Kuiper belt. So those color distributions are the same. But when you look at the centaurs that are close to the sun, inside the orbit of Saturn, the ultra-red ones are gone. So that is why I thought this idea that the Jupiter Trojans are thermally modified is a good idea. It's because you see this modification in the evolving color distribution of the centaurs as they come in. But that happens at 10 AU. And I think it's due to crystallization, the thing that we previously talked about. That's the right distance and the right temperature for crystallization to occur on these bodies. It will drive activity. It will blow out material, making a comet, but some of that material falls back on the surface. And it doesn't take very long to make an optically thick layer that covers up the ultra-red stuff. So I think that's happening in the centaurs. Something like that might have happened in the Trojans. But another ice line in Neptune's orbit?
Or, I mean, something that changes the surface, right? So, I mean...
Well, collisions would do it. Collisions would be non-thermal.
I mean, we don't really know what changing the surface color is, right? We think, but we argue that we know there's red and blue, but...
We do know they're red and blue. We just don't know what that means.
Exactly. We don't, right. So is it nature versus nurture? So could there be another, another degradation that you get sort of slightly blue, right? Where that, again, that's the region where Neptune's moving through. More,
yeah, I mean, just look at the histograms. That's all I got.
Yeah.
So make something up. Yeah. I'm just saying it didn't pan out the way, just like in the first mini talk, it didn't pan out the way expected. You know, I think that's interesting. So two freaks in a conundrum, that's what it's all about. Things that you don't expect, that are kind of surprising, or just plain puzzling, like this Trojan thing. Yeah.
The fact I'm booked all over time, but is the fact that the Saturn and Uranus don't have Trojans, I guess, is that relevant to this Nice model issue?
Well, the question is what is relevant to the Nice model? So the Nice model has a very messy. So Nice model predicted that the Earth would be ejected, right? You know about that. So first 5 years after the Nice model was published, certain individuals who shall remain nameless neglected to remind us that, oh, in this model, the Earth is ejected from the solar system. And when people started to say that could be a bit of a problem, they changed the model. they modified the model to keep the Earth stable. So that's good. But the point is the model has a lot of free parameters. And so you can get a lot of different results by tuning the parameters. So what does the Nice model mean? Nobody really knows. The Nice model also was proposed in 2005 to explain the late heavy bombardment, which is this time when the solar system received this heavy flux of projectiles 3.8 billion years ago. But, you know, the Nice model people in 2005 either forgot to mention or chose not to mention or did not know that the evidence for the late heavy bombardment was itself controversial. Like in the impact rate at 3.8, that's the late heavy bombardment. That sounds cool and fancy. We need to make a model of that. Or maybe it's just the tail end of a downward flux of impactors from much earlier times, from the formation epoch. And so they assumed that there was indeed a late heavy bombardment. They created the model to explain that by having Neptune torquing a massive Kuiper belt. And I agree, the model is spectacular because it has many free parameters. However, recent evidence from the study of zircons, which are like kind of very, very robust, high temperature crystals that you find in other rocks, survive from very, very early times, but which preserve through geochemical gradients, preserve kind of a temperature time history. Those zircon measurements provide no evidence for the late heavy bombardment, but they should. So again, it doesn't exist. So basically, the Nice model is able to explain things that didn't happen beautifully.
But I've actually counted that.
So then the question is, what does the Nice model mean? Yeah.
I mean, and how's admitted this, right? Hal Levinson's admitted that, right? The late heavy bombardment is a nice outcome of it, but it's not needed for the rest of the model.
Of course not.
Right?
Of course not, and that's the whole point.
Right.
It's
I
just
mean,
a
so I
parameter.
think that's the one thing. It's not the tunable parameter that they need to have it then. It's that's the.
You just tune a parameter and you can make anything happen. So now the argument is, and of course there's another paper saying, oh yeah, we never said it explains the late heavy. They simply move it closer to the origin of the solar system by changing the gap between Neptune and Kuiper belt. So you change the torque and you change the time scale, something like that. So you can do a lot with a flexible model. I'm not picking on the Nice model people. I think they're very smart, very thoughtful people in some cases. I am critical of this whole business of numerical modeling of systems. So I think what's happened in the last 20, 30 years is Moore's law has happened. So Moore's law has taken off, and it's allowing people to calculate incredibly complicated things without knowing what the hell they're calculating. That's the problem. So you can make models that have a lot of parameters that are vast and beautiful. You can make movies, which is the main reason we like the Nice model. It has beautiful movies, and they look like reality, but it's not reality. It's simulated reality. So it's moving into a kind of computer game arena. That's the problem. And it's not just astronomy either. It's all sciences are doing that. Computers now are able to do things that in a way are more interesting and more amazing than reality. And so I think there's a certain kind of person who gets sucked into that. And hey, you know, this model, it just assumes a life of its own and it becomes the new reality. That's what's going on. It's a psychological effect driven by Moore's law and the difficulty of obtaining high quality observations that can constrain these models. That's the problem.
I guess there's some, I would agree to some of that, but the broad strokes of the Kuiper Belt structure are explained by NEAS and Neptune migration. So
Well,
there are
the thing-
observables that we can represent that are
Yeah.
not
So
necessarily.
the great thing about the Kuiper
Right.
Belt, the discovery of the Kuiper Belt proves that there was planet migration. And so
Yeah.
before Kuiper Belt, nobody thought about that, nobody cared about that. But the fact that the resonances are so full of Kuiper Belt objects was unexpected, and yet was explained neatly, I think, only by the idea that Neptune scooted outwards and slid its resonances through the Kuiper Belt and picked up objects on the way, like a snowplow going through the Kuiper Belt. So that is the great triumph, I think, of Kuiper Belt science in the last 25, 30 years. The NEAS model takes it a step further and says, well, what if the planets migrated, because they migrate differentially, what if they migrated so much that even though they're not now in resonant orbits with each other, they once were? And so the key features of the NEAS model come from shaking up the solar system by making big planets, Jupiter and Saturn, cross into a mean motion resonance with each other. That's what the NEAS model is. And that's what I'm not sure about. Did that happen? I don't know. I know that Neptune migrated because I haven't heard any other ideas for populating the resonances. So the distance between the thing that I trust, which is the observation that the resonances are full, and the explanation, oh yeah, Neptune did it. I like that. That's all solid. But then the next step, yeah, the planets went through this major resonant interaction, and there used to be 5 giant planets in the solar system. Another parameter, you just stick in a giant planet. It's been ejected. Oh, there's another component to the asteroid belt we don't see anymore because, well, that was ejected too. There's so many degrees of flexibility in these models. There's so many assumptions are made. The jumping Jupiter model, even crazier is this grand tack thing, where Jupiter falls into the sun and is rescued at the last minute by Saturn, which goes in, attaches a hook and pulls the damn thing back out again. I mean, it's just nuts. Now, it doesn't mean it didn't happen. But what it means is, we shouldn't be believing this stuff like it's an observational truth.
No, I don't think anyone does.
I think some people do.
Okay, shall we wrap up?
Just one short question.
Yeah.
Since I don't study the solar system,
You're still on sabbatical.
generally, except for except for calibrators. But if
Was that an insult?
option
Was that
three
an
is-
insult? I think that was an insult.
If option 3 is the right one, can you say anything about the colors?
Then you would say, well, the colors probably just reflect the colors of the surfaces that were present in that vicinity. And the colors are not that special. The D-type asteroids are a little bit redder than the asteroids in the main belt, but they don't have this ultra-red material. So the idea is that the color difference occurs because out there stuff is cold and probably long-lived, and it's been made ultra-red by something, and that's something we think is cosmic rays. That's not necessarily true either. But in the inner solar system, somehow that can't happen.
So it sounds like a more plausible solution.
Hey, well, let's thank David.
Thank you.